The sun has already thrown a cloud of hot gas toward Earth, and the clock is running down as that cloud crosses the dark space between us. Tonight, the sky may answer with color, while satellites, radios, and power systems feel something they cannot see. But the strange part is not that the sun erupts, it is that a quiet-looking blast can sometimes hit harder than a much brighter one. And this August storm is showing us exactly why space weather is so difficult to predict. If you enjoy real space stories without wild claims, stay close, because the next few minutes will separate the danger from the drama. A quiet sun can still send a surprise our way, and knowing the difference helps you watch the sky with clear eyes. On August 8, 2026, the sun released two large clouds of material during eruptions called filament eruptions. A filament is a long, dark-looking ribbon of cooler gas held above the sun by invisible magnetic fields. When those fields break or twist too far, the ribbon can rise and blast outward into space. The cloud that follows is called a coronal mass ejection, or CME. That simply means a huge moving cloud of charged gas and magnetic fields leaving the sun. That burst may include a solar flare, which is a flash of light and radiation. It may also include a CME, which is slower but carries a great deal of matter and magnetic force. These two events can happen together, but they are not the same thing. A flare reaches Earth in about 8 minutes because light travels so fast. A CME usually takes many hours or several days because even a fast cloud is far slower than light. The August event is unusual because the sun looked quiet when the cloud was launched. There was no powerful X-class flare linked to the eruption described in the latest report. The strongest flare on August 8th was only a B 7.6 event, a weak flare by the sun's scale. That sounds harmless, but it shows why judging a storm only by the brightness of a flare can lead you in the wrong direction. Scientists do not rank CMEs by one simple number. They study the speed of the cloud, its width, its direction, and the magnetic field carried inside it. That last part is the hardest to know before the cloud arrives. A CME can look impressive in pictures and then miss Earth completely. Another can look modest from far away and still push Earth into a strong magnetic storm. At first, experts expected the August 8th eruptions to bring only a limited disturbance. The solar wind around Earth had already been settling, and the moving cloud was not racing toward us at an extreme speed. The measured solar wind speed during the earlier passage rose from about 250 kilometers per second to around 350 kilometers per second. In everyday terms, that is still unbelievably fast, but it is not the speed of the most dangerous solar blasts. What scientists found instead was a strong magnetic field inside the passing cloud. The cloud did not need to be the fastest object ever seen. It only needed to carry the right magnetic direction when it reached Earth. That direction made the difference between a weak brush and a serious push against our planet's magnetic shield. This is the first important surprise of the August storm. Earth is protected by a giant bubble called the magnetosphere. It is made by the magnetic field produced deep inside our planet. The bubble reaches far into space and turns aside much of the charged material flowing from the sun. Without it, the solar wind would strike the upper atmosphere much more directly. The magnetosphere is not a wall, though. It can bend, shake, stretch, and let energy enter. Picture the planet's magnetic field as a door between the sun and Earth. When the magnetic field inside the CME points the wrong way, the door can open more easily. Scientists call that important direction southward BZ. BZ is simply the north or south part of the magnetic field carried by the solar wind. If it turns south and stays that way, energy can pour into Earth's magnetic system. That is what happened during the earlier part of this August sequence. The magnetic field near Earth became stronger, and then BZ turned south for long periods. One southward interval lasted about 3 hours and reached -18 nanotesla. Another lasted more than 5 hours and reached -17 nanotesla. A nanotesla is a tiny unit used to measure magnetic strength, so those numbers may sound small even though the effect was real. Then the actual magnetic response climbed to G2, or moderate storm level. The planetary K-index reached 6 during the strongest period on August 8th. The K-index is a number from 0 to 9 that describes how disturbed Earth's magnetic field becomes over a 3-hour period. A KP of 6 means the planet's magnetic environment was disturbed enough to push auroras toward lower latitudes than normal. It was not a planet-wide emergency, but it was stronger than the first simple forecast suggested. Here is the detail many people miss. The storm was not powered by a giant fireball hitting the ground. Nothing from the sun punched through the atmosphere and landed on Earth. The main action happened high above us, where charged particles and magnetic fields pushed against the magnetosphere. The atmosphere and Earth's magnetic field absorbed most of that energy before it could reach the surface. Have you judged a storm by the size of the flash instead of the force behind it? If the magnetic direction surprised you, tap like and share your guess about whether auroras or technology will show the effects next. The first visible sign of a geomagnetic storm is often the aurora. Near the North Pole, people call it the Northern Lights. Near the South Pole, it is the Southern Lights. They appear when fast charged particles travel along magnetic field lines toward the upper atmosphere. There, the particles collide with oxygen and nitrogen high above the ground. Those collisions make the gases glow. Oxygen can produce green light, which is the color most people expect. At higher altitudes, oxygen can also produce red light. Nitrogen may create blue or purple shades, especially at the lower edge of an auroral curtain. The colors are not paint in the sky. They are the visible result of atoms releasing energy after being disturbed. During the August 8th storm, the strongest interval occurred between 18 and 21 UTC. UTC is a worldwide time standard, so it avoids confusion between local clock times. The KP index reached 6 in that window. Auroras may have been possible in places such as Toronto, Chicago, Boston, northern England, and parts of Scandinavia. But summer twilight made the northern show harder to see in some areas. That creates another twist in this story. A storm can be strong enough to send auroras south, while the local sky is still too bright for human eyes. In the northern hemisphere, August nights are short at high latitudes. In the southern hemisphere, winter darkness gives viewers more time. This is why the South Pole became one of the best places to notice the display. A webcam at Davis Station in Antarctica recorded active aurora during the night of August 8th and 9th. That station is part of the Australian Antarctic Network. People there did not need a dark northern summer sky to wait for the lights. The long Antarctic night provided a much better background. The same storm could be hidden by daylight in one part of the world and visible in another. Experts originally expected the first August CME to produce only a modest response, because the solar wind speed was not extreme. They knew a cloud was near, but they could not know its most important internal feature until it arrived. The magnetic field inside a CME is like the contents of a sealed package. Telescopes can track the package, but they cannot fully read the label from millions of kilometers away. When spacecraft near Earth measured the field, the picture changed. The cloud carried enough magnetic strength, and its direction lined up well enough to transfer more energy into the magnetosphere. That is why a forecast can say G1 is likely while G2 becomes possible. The wording is not a guess. It reflects a real limit in our ability to see inside a moving cloud. The sun also keeps sending smaller changes after a major event. Even when the main CME passes, the solar wind may remain unsettled. The magnetic field around Earth may continue to swing between north and south. That can create short bursts of aurora after the main show appears to be over. So the end of a storm is not always a clean line on a chart. On August 9th, the magnetic field had mostly returned to quiet or unsettled conditions. KP values stayed below 4 during that reporting period. That was a sign the strongest effect from the August 4th CME was fading. But 2 more CMEs from August 8th were still being studied for possible Earth-directed parts. Forecasters had to watch the new clouds while the old disturbance was still settling. This is where the storm becomes a live story instead of an old event. The question is not only what already happened on August 8th. The question is what the next magnetic turn will do when the remaining cloud reaches Earth. A small change in direction can decide whether the night stays quiet or lights up again. Space weather moves in waves, not simple on and off switches. The August 8th eruptions came from filaments rather than from a huge flare. That matters because a filament eruption can throw out a CME even when the flare signal is weak. The flare is the flash that cameras see first. The CME is the moving cloud that may arrive later. A weak flash does not guarantee a weak cloud. Scientists use several kinds of instruments to follow this process. The Solar Dynamics Observatory watches the sun in different wavelengths of light. Some images show hotter layers, while others reveal cooler structures and magnetic fields. The SOHO spacecraft uses a coronagraph, an instrument that blocks the bright face of the sun. This allows cameras to see the faint outer corona and the cloud moving away. From the ground, magnetometers measure changes in Earth's magnetic field. Satellites monitor the solar wind before it reaches the main atmosphere. Radar and radio systems can show how the upper air is changing. All of these tools form a chain of warning. No single sensor can tell the whole story. At first, experts looked at the quiet flare count and the fairly simple sunspot regions. On August 8th, no M-class or X-class flares were reported. C-class flares are stronger than B-class flares, and M-class are stronger still. X-class flares are the strongest group in the system. The absence of those large flares made the surface look less threatening, but the actual finding was that 2 filament eruptions could still send Earth-directed material outward. A filament can stretch across a large area while producing only a small flash. Its magnetic structure may hold the real power. This is why space weather scientists do not stop watching simply because the flare list looks calm. The surface can be quiet in one way and dangerous in another. The next clue came from the solar wind itself. Before the CME arrived, the solar wind was slow and calm. During the passage, it became stronger, and the magnetic field rose from a quiet level near 24 nanotesla to a higher level near 19 nanotesla at one measured peak. The numbers can look confusing because a field can change in different parts at different times. The important point is that the field became strong enough to matter. Once BZ turned south, the magnetosphere began accepting energy more efficiently. That energy traveled along magnetic field lines and helped power the aurora. It also caused currents to flow through the upper atmosphere and near Earth's surface. Those currents are usually small for people on the ground, but large storms can make them important for long wires, satellites, and electrical networks. Did you know that the part of the storm we cannot see, the magnetic direction, may matter more than the bright flash? If that changes how you think about solar storms, leave a comment with the one number or term you want explained in plain English, then follow for the next update. For most people, a G2 storm is not a direct health danger on the ground. Earth's atmosphere and magnetic field provide strong protection. The risk is higher for technology that operates above the atmosphere or stretches across large distances. That includes satellites, navigation systems, radio links, and some power equipment. The effects depend on the strength, duration, and location of the disturbance. Satellites can feel a storm in more than one way. Energetic particles can charge the surface of a spacecraft. That charge can cause temporary glitches or, in rare cases, damage sensitive electronics. A storm can also heat the upper atmosphere and make it expand slightly. When the atmosphere expands, it creates more drag for satellites in low orbit. More drag means a satellite can lose altitude faster than expected. Controllers then have to update its path. The International Space Station and other spacecraft are built with protection and procedures for space weather. They do not simply float helplessly when a storm begins. Teams receive warnings, check instruments, and change plans when needed. Navigation signals can also change. GPS satellites send radio signals through the ionosphere, a charged layer high above Earth. A storm can make that layer uneven and disturbed. The signal may then travel through a different path or arrive with a small delay. For a phone map, that may mean a little less accuracy. For aircraft, ships, survey crews, or emergency teams, small errors can matter more. High-frequency radio is especially sensitive to the sun. Radio operators use the upper atmosphere as part of a long-distance path. When that layer changes, some signals can fade, bend, or vanish. A powerful solar flare can create a radio blackout on the sunlit side of Earth. A geomagnetic storm can create a different set of problems later, as the magnetic field becomes disturbed. Power grids are connected by long lines that can act like giant antennas for changing magnetic fields. During a strong geomagnetic storm, currents can be induced in those lines. Grid operators monitor the changes and can adjust how systems are used. Transformers and other equipment are designed to handle many ordinary changes. The biggest storms are the concern, because they can push systems outside normal conditions. The August event reached G2, not the highest level. That distinction matters. A G2 storm can create real technical effects, but it is not the same as an extreme G5 event. Words like dangerous, historic, or catastrophic should not be used for every aurora alert. Clear warnings help people prepare without turning normal space weather into panic. The rare part of this August storm is the mismatch between the quiet flare signal and the stronger magnetic response. The sun did not need to produce a famous X-class flare to create a beautiful and useful warning. It only needed to release a cloud whose magnetic field interacted well with Earth's field. That is a subtle process, but it controls the outcome. There is also a lesson in the timing. A flare can be seen almost immediately, but the CME takes time to travel. That delay gives forecasters a chance to study the cloud and issue warnings. Near Earth, spacecraft can provide a final alert only minutes to about an hour before the strongest impact. The exact warning time depends on the spacecraft position and the speed of the solar wind. This short warning window is why prediction remains difficult. Scientists can watch a CME leave the Sun. They can estimate its travel time and likely path. They can compare it with models of the solar wind. But the last magnetic direction can still surprise them. The cloud may rotate, spread, or mix with other solar wind structures during its journey. Imagine trying to predict a wave by watching it from far away. You may know when it will reach the shore and how large it looks in the distance, but the shape of the beach and the angle of the wave decide how high it rises. Earth's magnetic field is part of that shoreline. The CME is the wave, and BZ is one of the features that decides how much energy reaches us. Now look back at the early expectation. The first forecast called for unsettled or active conditions and a chance of an isolated G1 period. That was reasonable based on the available evidence. The actual system reached G2 because the magnetic conditions became more favorable than the simplest estimate. This is not a failure of science. It is science updating its answer as new measurements arrive. The current forecast for August 12th called for unsettled to active conditions, with a possible isolated G1 and even G2 period. The reason was the expected arrival of material from the August 8th filament eruption. For August 13th, forecasters expected quiet to unsettled conditions, with KP possibly reaching 4 as the CME effects faded. KP4 is below the G1 storm threshold, but it still means the magnetic field can be active. That forecast does not promise an aurora for every location. Aurora depends on darkness, clouds, light pollution, latitude, and the direction of BZ. A storm can be measured by instruments while the sky looks completely normal to most people. A bright aurora may appear in one region while another region sees nothing. Space weather is global, but the experience is local. If you are watching the sky during the August alert, choose a dark place away from city lights. Give your eyes time to adjust. A phone camera may detect color that your eyes cannot see at first. Look toward the northern sky in the northern hemisphere, or toward the southern sky in the southern hemisphere. Do not stare at the sun to look for the storm, because the aurora happens at night and the sun can harm your eyes. Clouds are a bigger problem than many people expect. A strong magnetic storm cannot shine through thick cloud cover. Weather forecasts and space weather forecasts must both cooperate. A clear sky under a weak storm may show more than a cloudy sky under a stronger one. The best plan is to check the local sky, the darkness, and the aurora forecast together. The NOAA Space Weather Prediction Center tracks these alerts and posts measurements of the planetary K index. Its scale labels storms from G1 minor through G5 extreme. The scale is meant to describe effects on systems, not to predict a perfect view from your backyard. Other services may turn the same data into simple maps or phone alerts. Always check the time and location attached to an alert. A common mistake is to read the word storm and imagine a wall of radiation falling through the sky. That is not what a geomagnetic storm means for someone on the ground. It means Earth's magnetic environment is disturbed by energy from the sun. The atmosphere remains above us, and the magnetic field continues to protect the surface. The main concerns are technology, operations, and the chance to observe an aurora. Another mistake is to believe that every solar flare points directly at Earth. The sun is always producing some level of flare activity. The flare must be in the right direction to affect Earth's dayside radio environment strongly. The CME must also be aimed toward Earth to create a geomagnetic storm here. Direction matters as much as size. A third mistake is to assume that an X-class flare always creates a major geomagnetic storm. A powerful flare can produce a radio blackout without sending a large CME toward Earth. A CME can miss us to one side. A weaker flare or filament eruption can send a cloud along a path that reaches us. The sun does not use one single danger meter. In the days before August 8th, the sun showed several active regions. Active regions are areas where magnetic fields are concentrated, often around sunspots. Some regions were labeled AR4503, AR4504, and AR4505. The letters and numbers are tracking names, not scores. They help scientists know which patch of the sun produced a flare or changed over time. AR4505 became a leading flare producer after emerging on August 9th. It produced many small B and C class flares in the following period, but it was already close to the western edge of the Sun as seen from Earth. Because the Sun rotates, that region soon moved out of view. A region leaving the visible side may still be active on the far side, but its eruptions are less likely to point at us. AR 4503 and AR 4504 were simpler and quieter. AR 4506 appeared in the northeast area and showed stable behavior in the latest report. The lack of complex magnetic shapes reduced the expected chance of a large new flare during the forecast window. Still, the Sun's far side can hide regions until rotation brings them around. That is another reason the forecast can change. The real-time problem is not that scientists know nothing. They know a great deal about solar wind speed, magnetic strength, particle energy, and field direction. The problem is that the key data arrive in stages. First comes an image of the eruption. Then models estimate its path. Later, spacecraft near Earth measure its actual conditions. Each stage narrows the uncertainty. As the CME passes, the magnetosphere may compress on the sunward side. Its tail can stretch far away from Earth on the night side. Particles may become trapped in belts around the planet. Some travel down toward the poles where they create auroras. The system can ring like a giant magnetic instrument after it receives a strong push. The sound of that process is not something human ears hear in space. Space is too empty for ordinary sound to travel. But instruments can turn magnetic changes into data, charts, and even audio tones. Those sounds are translations of measurements, not the actual noise of a storm. The event is silent to a person standing outside, yet active in the space around Earth. This is why satellites are not just watching the storm for us, they are also part of the warning system. A spacecraft farther from Earth can detect the approaching solar wind before the cloud reaches our planet. A spacecraft closer to Earth can provide a final reading of the magnetic field. Together, they give operators a short chance to react. Would you rather see a faint aurora from a quiet storm, or a bright aurora from a storm that disrupts technology? Tell me which trade-off you would choose, and if the question made you think differently, leave your answer and pass this story to another skywatcher. There is a human reason to care about these forecasts. Modern life depends on systems that cross space and distance. A navigation signal may guide a rescue team. A satellite may connect a remote community. A radio link may carry information when cables are damaged. The invisible environment above Earth has become part of everyday life. The August storm is a reminder that our planet is connected to the Sun. We live under a star, not under a perfect roof. The same light that warms oceans and grows plants also sends out magnetic clouds. Earth's protective systems make life possible, but they do not make technology immune. Understanding the connection helps us build better warnings and stronger equipment. There is no need to fear the sky because of a G1 or G2 alert. Fear is not a useful forecast. Attention is useful. Check official updates if you operate satellites, aircraft, radio equipment, or power systems. If you simply want to watch the aurora, prepare for darkness, clear weather, and the possibility that the show may not appear. Nature does not owe us a perfect display. A storm can peak during daylight. BZ can point north when the cloud arrives. The cloud can weaken before reaching Earth. Clouds can cover the sky. Those are not signs that the forecast was a trick. They are part of a system that changes from hour to hour. At the same time, the storm can become stronger than expected. The August 8th event already showed that pattern. A modest-looking eruption created a CME with a strong magnetic field. The field turned south for hours. The KP index reached 6, and auroras appeared in the dark south polar sky. The result was bigger than the quiet flare count suggested. The next major reveal is not another number. It is the fact that the storm gives us a test of scientific patience. We want a simple answer. Will it hit? How strong will it be? And where will the lights appear? Researchers can answer each question only as well as the incoming measurements allow. Good forecasting means giving a range, then changing it when the evidence changes. On August 12th, the remaining effects of the August 8th eruption were expected to create unsettled to active conditions. A short period could reach G1 or G2 levels. By August 13th, the storm was expected to weaken toward quiet or unsettled conditions. But a forecast is not a promise, and aurora viewers should check the newest update close to the time they plan to look. This is also why old storm stories can become misleading. A page may have a familiar title and an August date, but the year matters. For example, a NOAA page titled G1, Minor Geomagnetic Storm Watch for August 28th and 29th, describes an event from 2022, not the current 2026 event. The same month and similar words do not mean the same storm. Always check the publication date before trusting a dramatic alert. Space weather has a memory problem because the sun repeats many patterns. Solar cycles rise and fall over about 11 years. Active regions return, flares repeat, and CMEs appear in different seasons. A headline can sound current even when the event is old. Reliable watching requires the date, the source, and the measured data. The August 2026 event also shows why the word rare should be used carefully. Geomagnetic storms happen regularly when the sun is active. What feels rare to an observer may be the combination of timing, darkness, location, and a strong southward field. For someone in Antarctica, the aurora may be a remarkable winter view. For someone in a bright northern city, the same storm may pass unnoticed. So what should you know before the next alert? First, a CME is a cloud of solar material and magnetic fields, not a ball of fire falling onto Earth. Second, the magnetic direction, especially southward BZ, can control how much energy enters the magnetosphere. Third, G1 and G2 describe levels of geomagnetic disturbance, not a simple danger rating for every person. Fourth, the KP index measures global magnetic activity over 3-hour periods. A KP of 6 means a moderate storm and can push auroras toward lower latitudes. Fifth, a good aurora forecast still needs a dark, clear sky. Sixth, technology operators should rely on official warnings because satellite, radio, and grid effects depend on local systems. Seventh, forecasts can change after the CME reaches spacecraft near Earth. That is not a weakness in the science. It is the moment when direct measurements replace distant estimates. The last part of the journey may reveal the field direction that cameras cannot see clearly from the sun. If the clouds clear tonight, look up with curiosity, not panic. You may see nothing, or you may see a pale green curtain moving silently above the horizon. Either result is part of the same story. The important event is happening far above the weather, where Earth's magnetic shield meets a wave from the sun. And if you do see the lights, remember what created them. The color comes from atoms in the upper atmosphere. The motion comes from charged particles guided by magnetic fields. The energy began with a change in the sun's magnetic structure. A chain that starts millions of kilometers away can end as a shimmer above your own town. That connection is bigger than a single August forecast. It links solar physics, spacecraft engineering, power planning, radio science, and human wonder. It reminds us that Earth is not isolated. We are part of a space environment that changes every day. Most of the time, our planet handles it quietly. Sometimes, the sky shows us the proof. The August storm is not a reason to imagine the end of the world. It is a reason to understand the real world more accurately. A weak flare can hide a strong magnetic cloud. A moderate storm can produce a beautiful aurora without threatening people on the ground. And a forecast can become better when scientists admit what they cannot know yet. Before you leave, tell me this. If you could stand under one clear sky during this storm, would you choose Antarctica, northern Canada, northern Europe, or somewhere else? Subscribe if you want the next space weather update explained without exaggeration, turn on notifications so you do not miss the next change, and share this with someone who watches the night sky. Your comment may help another viewer understand why the color above Earth begins with a magnetic disturbance far away on the sun. Thank you for watching. Stay curious about the sky and keep looking up with wonder today.